Awesome. Good to see you, everyone. This is another fun adventure with Deep Learning Adventures. We're a fun community that explores interesting topics around deep learning and machine learning in general. My name is George. I'm joined by many great friends and colleagues from around the country, especially my co-organizers and co-hosts, David and Robert. Today, we're going to talk a little bit about a cool topic called Data-Centric AI. And for those of you joining us for the first time, or those of you who are joining us from YouTube or other social media, you can find us on Meetup under Deep Learning Adventures. We have a YouTube channel as well. Let me find it here. Today's session is recorded and will be posted under this guest speakers. I think it was the one that felt more appropriate, but we have, just to give you an idea of what content we have. We've covered different topics. We've covered several Coursera specializations on machine learning and deep learning. We covered some special topics like attention transformers. This is a specialization that we covered in the past. And this was an interesting one of Kaggle courses where we tackled different data science projects from scratch. Anywhere from Python, SQL, data visualization, beginner level, intermediate level machine learning, ethics and AI, bias and AI, all these cool features, as well as some hands-on projects that we have here on different structured and unstructured data set, time series, NLP, computer vision, and so forth. Yeah, really fun community. Thanks for joining us. And right now, just to give you some more context, we're in this Amazon Web Services specialization track. We took the entry-level specialization called Cloud Practitioner. We passed it, and now we're studying for the machine learning specialization. And we had a session here that we recorded. Feel free to check it out on the resources we're using. And this is a little bit more intense and more demanding than the Cloud Practitioner, so it's taking us a bit longer. But hopefully, pretty soon you're going to hear from us that we took it, we passed it, and we're happy to share some comment with you and the overall community online. Cool. I'll post this in the chat for you joining us for the first time, and also in the Meetup page, I'll post the Slack channel where you can join us on Slack. We have several channels there. If you're looking for new opportunities or new roles, we have an opportunities channel. We have an events channel where you can look at or post your events or look for events that are interesting to you. But switching back gears to today's topic, we're going to talk about Data-Centric AI and what that is and some resources that we find useful. Okay, so I have mentioned all the resources. We've mentioned all the resources here. I have opened several tabs here. I'm just going to briefly introduce the topic and then hand it over maybe to Robert or David or really to anybody who has maybe read more about this. But this is a shift in the way that we think about machine learning and deep learning specifically, where I think there's a frame here in this video that I like, so from Andrew. So let me see if I can find it. I find it really interesting. So most of us think of AI as what? As code plus data, right? And for many decades, maybe for the last 2 decades, everybody's been focused really heavily on the code part. We have this assumption that we freeze the data. Let's say for any, let's say for example, for a computer vision task, we freeze the data, and we spend all our efforts into tweaking the code, picking the right algorithm, picking the right model, picking the right hyperparameters, picking the right execution, how is it trained, where is it deployed, how is data fed, and all that. But basically, we spend a lot of time in this code part, which is basically software that runs on infrastructure like GPUs. And we hope to improve, whatever our metric is. If it's accuracy, we hope to improve accuracy. If it's object detection, we hope to improve that in terms of not only detecting the right classes, but also the bounding boxes around them. But this data-centric shift, and it's really a monumental shift that Andrew is mentioning here, is you keep the, so let me find the right frame. You keep the code the same, you freeze it. Let's say you pick a specific computer vision architecture like ResNet 50 or a simpler one like VGG. And you actually try to manipulate the data in a way that will increase your performance. So for example, if this is like a classification task, what kind of feature engineering can you do? What kind of data augmentation can you do? What kind of noise reduction can you do on the data itself so that you can improve your metric? So in very brief words, this is like the shift from a model-centric approach to the data-centric approach. I'll pause here for any comments or suggestions or input. But I just want to clarify that this is what we're talking about. So it's a discipline where we systematically engineer the data to build an AI system. So we're specifically focused on data instead of the code itself and the model.
So I think there's really great value in this. I think it's interesting. One thing I would say is this is really geared toward deep learning. Machine learning in general, the more classical machine learning methods, because they haven't really had a lot of advances in many years, right? The models themselves, they've had a little bit more of a focus on data, particularly like feature engineering, things like that. So I think they've been a little more data centric than the deep learning crowd. So this is a big shift for deep learning, even more than just classic machine learning. At least that's my.
That's a good observation. Yeah. Usually when you hear like boosted trees and all that, especially in competitions, all the effort is in feature engineering. 99% of the effort is in feature engineering, and just pick like a out of the box boosted tree, like GBM, and that usually gives you good results.
I can't remember where I heard it, but somewhere I've been familiar with this description of deep learning models as a combination of 4 inputs, right? There's data that goes in, there's a decision on what your architecture will look like, there's a choice of loss function, and a choice of how to probe the model space, meaning an optimizer, how to optimize that. And most deep learning approaches have involved manipulating some combination of these things. Maybe you change the architecture. You don't always change the loss function that much, but you might play with the optimizer, and then you'll have some data augmentation. So you'll have some combination of these things. So this concept of really just focusing on one of the 4 and leaving the other 3 constant is kind of novel.
That's interesting too. Yeah. Usually when you do hyperparameter tuning, right, you might tune the optimizer, maybe you try different optimizers, but usually you keep the loss function the same. Usually play with learning rate or weight decay or some kind of scheduling or some kind of basic optimization techniques. But yeah, that's interesting. Okay, before we go to other topics, I just quickly wanted to share with you something that is available here in the DataCentric AIorg, which is a resource that is specifically created for this concept. And there are these 3 interesting articles here, and feel free to check them out. I'm not going to dive too much in them, but I'm just going to pick from them something that struck me when I was reading them. One is the idea of basically switching from data labeling as a service to data labeling as collaborators in a machine learning project. And this is like a very simple example, an NLP example where a crowdsource, a group of users is asked to classify the comment as toxic or non-toxic. And this could be very subjective. But there are two sentences, and the first one says, "People still eat at Pizza Hut, something gross. It is shameful how this country, blah, blah, blah." And then you have some different, reasons why people might think this is toxic or not toxic. It's like binary classification at this point for this sentence. Some of them, take it out of context. Some of them are only looking at this specific context. So basically, the long story short is that half the people think it's toxic, half the people think it's not toxic, or maybe a third, and the other third is, it depends on the full sentence. So
this actually becomes a really interesting data example in the context of some of the recent global events where the Facebooks and Instagrams are constantly updating their definitions of what speech should be permitted and not.
Right. Yeah, that's an interesting correlation. So some steps that this article is recommending is that before you, and before I talk about the steps, this reminded me a lot of the project that we did over the summer last year. For those of you joining us for the first time or recently, we had a object detection project that we did last summer where we were trying to detect our faces. We actually collected our own data, we labeled them, we annotated them. We used our own models and we deployed them on our computers as well as the mobile device. But a lot of the lessons here, I think we can relate to, and you'll see once I go through that. So first things first is, before you hand over, let's say you have thousands of images to be annotated or thousands of sentences to be classified as toxic or not toxic, whatever your task might be, make sure you yourself, as a project person or leader, go through the labeling process by yourself. And there are two reasons. One is, first of all, this will give you an idea of how challenging the task is, but most importantly, this is how you're going to be used. This is how you'll be exposed to the nuances of the data set. So you might find some easy examples like, okay, I can classify this as toxic or not toxic, but you might find some really interesting and not so easy examples that you need more context. So first step is, you yourself should go through this effort. And this is a way of, as you'll see, of systematically treat or improve on your data and collect and process your data so that you can have better performance in your AI project. Then it talks about, treating your workers as, as collaborators. So it says a lot about the cost, and, if you use services such as Amazon Turk, depending on how expensive the task is, you might get more interest or some interest. So it talks about that as well. It then talks about small pilots, and it makes some analogies with launching a software program that, when you beta test it, basically have a small team that can find all the issues pretty quickly instead of launching it to the world. So they just mentioned an article here that, like, when you develop something in software, most usability bugs can be caught up by 5 to 7 people. Then the other thing is, when you get back the results and when you are evaluating them, because you need to evaluate, you shouldn't assume that the annotators did an excellent job and your data set is in 100% good, clean state to be used by your model. When things don't go as expected, so let's say when there's a toxic comment, but your annotator did not annotate it properly, usually think, okay, what's wrong with this annotator? But that's because you come from your perspective, and this article is suggesting that instead of saying why weren't they paying attention, you should switch the context to what did I do wrong in communicating my intent. So something maybe was lost in translation or in communication. Maybe my task or my intention was not communicated properly to these annotators. if you can actually access this group of annotators, let's say you have an internal team, this is doable only in that case. You can actually say, things like, yep, you got it. The answer was this, and this is the reason. So you're basically training your annotators to understand better what is your intention. And this dives a little bit more into this collaborative approach where for large complicated projects, it is best to actually hire a small team and train them instead of relying on a large crowdsourcing platform. And this article mentions 2 specific projects here, one in NLP and another one in computer vision. Yeah, there was an interesting project where they were trying basically to not only detect objects in an image, but also create what is called the scene graph of relationship of objects or items in the image. So for example, there's a person here, he's walking, where on the crosswalk, or there's a person here playing the guitar, wearing sunglasses. Also, the sunglasses are hanging on a stand, in a wooden stand in the background. Like, this was an interesting project. So the summary was that if they actually work with a smaller team and they train them properly how to annotate these images, the project would have moved much faster and at a smaller cost. Yeah, that's this article. I find this very interesting. Data augmentation, we've seen it multiple times. I'm not going to dive too much into this. Feel free to read this, but basically using your data or maybe using synthetic data is a way to improve, to increase your data set. And this concept of domain gap, data bias, and data noise, where domain gap basically says that you're training your model on a specific data, but that's not the data the model will be exposed to in the real world. So there's a domain gap. You're training it on nice sunny days in California, let's say self-driving cars, but then you take it somewhere else and it's rainy or moisty, or there's fog, and that's not the real world scenario. Or you might have bias. Your data set might be biased based on the way that it was collected, or it might be specific noise. Cool. And last one, this was an interesting article. I quickly skimmed into it, but most of us, when we talk about machine learning, we tend to spend a lot of time in the code itself, but actually there's a whole infrastructure, right? Especially for larger companies, right? If you actually roll out this in production, of how do you configure all this project? How do you do the data collection? How do you verify it? How you do the feature extraction or the feature engineering? How you analyze what your model is output? How do you serve it? How do you, how do you expose it to the world through an API, or if you embed it somewhere? How do you monitor it in case the data is, maybe a data shift or data distribution shift, or maybe something is off in any of these components? And you see the ML code is a very small part of this process. So this idea of technical debt was interesting here. Yeah, data quality. This data sheets, I think we might have seen this in one of our Kaggle courses, but Tim H. introduced this idea of data sheets, and I'll open this paper here just to get an idea. But this was an idea of how do you actually systematically, I'll go all the way to the end of this paper, there's a data sheet. How do you describe a data set, and how was the data collected? Like, what is the motivation for this data set? Who created it? Who funded it? And then what is it made of? Like, some specific information about it. Collection process, over what time? Did you collect it directly? Did you do any pre-processing, any cleaning, any labeling? How are you sharing it with others? How are you using it, and so forth? I find this interesting. It's how you're maintaining it as well. So yeah, check check this out. Okay. I think that's it. Before we switch gears, there was a workshop. I don't know if there was one or two, but there was definitely a Europe's workshop last December. A lot of, there was a call for papers. I find this part of the Europe's interesting, but basically gives you an idea of what approaches or what is new basically in data-centric AI. And it is broken down into tools and methodologies, algorithms, and responsible AI. And most of it is under here, tools and methodologies. So it was calling for papers that have new ways or have developed tools that quantify and accelerate time to prepare high quality data, where you label consistently, improve data quality, automate creation of high quality training data, and so forth. You see the theme here, as well as how do you import or how do you combine multiple data sets, how do you export them, how can you use them with architectures like MLCube and Airflow. And the algorithms, what data selection techniques for active learning are used. Maybe you should do like a topic on active learning. I find it fascinating. Transfer learning, how do you detect drift and all that, as well as fairness bias, green AI for energy consumption, scalable, reproducible, the data cards that we saw earlier, and so forth. I found this breakdown really interesting. It gave me an idea of what they were looking for, and there was actually a competition. So this was the Europe's part, but they're actually Landing AI and DeepLearning AI collaborated on hosting this competition of freezing the model and just manipulating the data. And here are the entries. And I think I'm going to hand it over to David just to give us a bit more background about this competition.
Yeah, can I share my screen?
Absolutely. Share screen.
All right. So DeepLearning AI and Landing AI sponsored this competition that took place last year, and I believe it ended in September. Landing AI, if you're not familiar with them, they work with manufacturers to help them use AI in their different processes. It's one of Andrew Ying's companies. And then, of course, the education company on his side is DeepLearning.AI. We've taken many courses through Coursera that were designed and delivered by DeepLearning.AI. But so along with this concept of deep learning AI, they put a contest out there. And the idea is very simple. It goes along with the same concept Stuart's been talking about, where in this contest, you're given a model, and it's already defined as far as the architecture and everything, and it's not it cannot be changed, right? You're not supposed to work on any of the model's hyperparameters or any of that. They do the training here with some scripts they have, so you have no control over those other, Robert talked about the 4 different aspects that are normally optimized in deep learning. Well, 3 of those are frozen in this contest. So the only thing you can work on is data. In this contest, you're given Roman numerals. So we've all seen MNIST, where you have a data set that's Arabic numbers from 1 to 10, or sorry, 0 to 9. Here, you're using Roman numerals. And they give you a data set, an initial training data set of about, I believe it's about 4,900 samples of Roman numeral images. And they give you these scripts in here where you can then run the training and run against the test set and get your results. You're allowed to create your own training and validation sets to input to these scripts. And so the whole idea is to work on those, the training data and your validation data to optimize performance. As I mentioned here in the rules, they're pretty straightforward. Your submission, you're given those original 4,900 images to work with, but you can add to your training and validation up to 10,000 images. So you can have 10,000 combined images. And then they had a couple of different ways they judged. They judged on the best overall performance on the test set, as well as the most innovative strategies to do this. And what I wanted to do was maybe go through, Stuart said they have the list of the leaderboard there. And the part of this, I believe they were asked to write a post about what their approach was and everything. And so that's available online. And I wanted to go through the top 3 because I thought there was some really interesting things they did here that we can learn a lot from. So the very first one was a couple of guys who called themselves Symnapsynaptic, ANN or something like that. I'm not sure what the company is. And they tell a little about themselves. You can go through that, but then they start to go through the techniques. That's what I want to get at. So for almost all the entries, everybody did some manual data cleaning. They did this where they removed outliers, any noisy images or ambiguous images. So they manually went through these, 2,900 images and pulled out about 200 of those. And that's one of their data sets they're going to use to train with. They then asked their family to write Roman numerals. So family and friends, they got about another 4,300 images from that. I called this manual data augmentation.
Right.
So it's kind of a neat technique. So they got that set. So that was another set they added. And then the third one is one where they made a set of images that had the same distribution as the label book. The label book, I couldn't quite find out when I read through all the competition stuff what exactly they're doing here. I think what they did was they looked at the what was in the distribution that was in the original set of data that you get from deep learning, and they tried to reproduce that in their manual set, and so they called that their third one. So the details weren't enough here for me to quite pick out how they did this third set. But I think they were just trying to hold the distribution.
What was the difference between the third and the second set? The second one is their families, right? Age.
Yeah, the second one was just their families doing it. The third one was the distribution of the data. It's right. It had to do with, sorry, the third one, not the distribution, it's the label book distribution. So they look into this thing called the label book, and it's described here. Basically, they try to look at the way the images are in there, and they looked at all their other images and tried to find ones that were similar. It wasn't clear to me what they used to make that judgment, or if it was done manually. They may have been doing it manually again, but they didn't describe their method for selecting the ones, but they tried to get a very similar distribution. And the label book comes from deep learning. So their assumption was that the test set would have a similar type of distribution. So they're trying to replicate some of that.
A distribution over some ancillary labels that they're giving to the data,
Yeah,
such as lowercase versus uppercase or something?
something like that. That's exactly right. But it looks like they did more like the style that was in there too. They tried to, the actual style of the writing. I'm not 100% sure how they did that unless it was done manually. They didn't really talk about it.
They did briefly mention, I saw you scrolled past, it sounded like they were exploring generating some of this stuff with GANs.
Yeah.
Yeah, they thought about doing some of the augmentation with GANs, but they just didn't have the computational power to do it, so they gave up on that.
And could introduce some other problems.
Right. So they come up with these three different sets of data, and they're going to use those together. They then start applying some more automated type of augmentations. They're going to do 5 different types of crops of the images. They're going to do some aspect ratio standardization because the model itself is a ResNet 50 and it requires 32 by 30 pixel size. So they're going to do that. And then they apply some more auto augmentation to do some more traditional things, such as scaling and things. Interestingly, they found that the types of augmentations done on the SVHN data set, they use this basically the same ones, and they found that that was very fruitful for their getting their results. And then here's where I thought they maybe didn't quite stay with the spirit of the competition, in my opinion. So they've produced about 70,000 training images with those 3 data sets that they've made, and they need to cull those down to only 10,000, right? So they've got to somehow go through there and do that. And so what they did was they used a voting ensemble of other convolution networks. So they used other models to vote on what the proper label for all of those images were. And then any of them where there was a lot of problems, like all the models would get the wrong label that was considered to be a very noisy or ambiguous image where they couldn't get a good value. They would remove those. So that helped them get through a lot of these. And then they did another very interesting thing, which is they used what they called a threshold to determine, based on the probabilities that all those models came up. They talk about how they determine if it's noisy or ambiguous. It's a way of doing manually cleaning and getting rid of bad labels, noisy labels, and that saved them a lot of time and really helped them reduce their data down from a lot.
I'd say that's very much within the spirit of the competition, Like eventually, at the end of the day, you're just looking for images to feed back into the original unchanged model, right?
Yeah, but I kind of think it's interesting to use a model that's better than the one that you're going to use, right? It's kind of like you, I don't know. I kind of go back and forth. I'm like, well, this is great. It's within the rules. There's no, and it's very interesting idea to clean data this way.
Mm-hmm.
I did find it like a little disconcerting that they use more powerful models than the one that they're actually going to be competing with. So it was, I could go either way there.
Well, yeah, but sorry, the ResNet was the relative to the competition. That's more of advanced compared to what AlexNet is the very basic one. LeNet is very basic. I don't know what
there's a couple. Yeah, there's a couple here.
But VGG, yeah, all of them are much simpler than ResNet. So yeah, I see what you mean as well.
Remind us what the competition model was.
I believe ResNet 50.
So these are simpler than that one.
I think they are simpler in this case. Yeah.
Although it is an ensemble of multiples.
Right. Anyway, I thought it was it's a cool idea. It saved them a lot of time, doing this manually. So, but it does get to that idea of looking very closely at not only the predictions, but the probabilities that go with your predictions, and using that, to your advantage.
Right. So they basically got rid of the hard labels, right? The hard images, right? The ones that the models weren't sure of. There was no consensus, or they got it wrong.
Right. So they were either hard in terms of they were kind of ambiguous, like the image, like the 3 and the 6 or the 3 and 8 or something looked really close, right? So it was hard for the models, or they were just mislabeled, right? So if all the models chose 3 and the label was 8, then you probably want to look at that one. It might actually be 3, not be 8, right?
Right.
So it helped them also identify mislabeled ones, because a lot of these were generated by humans, right? So they were, or labeled by humans, so could be mistakes in there. So it saved them a lot of time. So that was the third best approach.
Sorry, is there anything in the end? Did they get any metric or feedback from the competition?
Oh, sorry. The scores are over on the other page that you showed.
Okay.
But they do kind of like, they do, it's interesting. They give advice for people how they might approach some of these things. So they kind of give, it's interesting to read through their whole thing. I just don't want to take all of our time here to do that. But so highlights from the second one. The second one was another team Inotescus. Don't know anything about them, but they again started with data labeling. They did manually remove noisy images, ambiguous images like these, which you couldn't tell what they were, and they removed some mislabeled, some incorrect classes. So that was all done manually. Then, I'm sorry, they did what I thought next was very interesting. The training set happens to be pretty imbalanced, so they wanted to rebalance it, but they didn't just do what we might do, look at some way of cutting down things and all that. They actually did this interesting thing. Let's see, I was trying to say, where what they're going to do is they're going to use some clustering methods to look at distributions of uppercase and lowercase labels. So not only, we may have pretty good balance between our labels, but the actual images can be upper or lowercase, right? And so we need to balance that as well. And so they did some clustering to identify how many of each they had. And from there, then they used some rebalancing, some techniques to rebalance those. For instance, when they, at one point they had 90 images with lower class 1 and 194 images with the upper class 1. And so they want to balance that, right? So in order to do that, they do that. So they do augmentation on that cluster of images. So if they needed like the lowercase 1, they needed more of those, they would do augmentation on those to bring it up to the same balance with the uppercase ones.
Now, they know nothing about the, say, case balancing in the test set, though, right?
We don't know anything about the test set at all. They've only given this training set to us that we can, we can augment,
They're only basing their decisions on how to balance it based on performance on their own validation set or subset from the training set.
Yeah.
So if they see that it's poor performance on the lowercase ones or something, they'll try to rebalance it.
That's right. Yep. And the only thing again here, they're actually using a better model, or no, they're using the same model actually. Sorry, right here they're using the same model. So to get their embeddings, they're doing that PCA reduced. So I thought it was interesting that they do it at the embedding label and not anywhere else, right? So it was kind of fascinating to see that. They go through it a little bit.
So that's the model I actually use for
this is the model. Yeah, this is what the one you're given.
But they use it for embeddings.
Okay. To then do their balance, to do the balancing. Yeah.
Okay.
So before they did the clustering, they did PCA with this embeddings to do to get their clusters right. It's an interesting approach. It was novel to me. And here I thought was a pretty very important thing where they do what I would call error analysis, where you look at your results and you see what are you missing, like what are the labels that you're missing, the classes you're predicting wrong, right? And you look at those examples very closely. And so here they determined that a lot of the ones they were missing were edge cases, where there was very hard examples and augmentation around that. So they picked, they wanted to put more of these type of cases into the training, so the model would get better at training on them. And how they identified these, I thought was really neat. So they actually created this thing called a difficulty score, where they look at the the top 2 probabilities in the classes that go with those, and when those are close, very close, that's considered to be a very hard choice, right, for the model. And so they actually then sort all the images in the data set based on that, the ones with the high difficulty scores. Here's some examples of things that I don't know if they're close or what, but sometimes there was just really a lot of disagreement about what these might be. So they had a high difficulty score, but they know what the true label is, right? So that allowed them to put in an additional, they did some augmentation on these, and that allowed them to put in an additional 880 hard images. And then they randomly removed 880 what they call easy images from the data set. And so that allowed the model to get better at those very, at these ones, which apparently are quite hard for the model. One thing they did do here, I thought they didn't do a lot of any other kinds of augmentation. They did when they were doing the rebalancing, that's when they threw some augmentation in with translation, scale, and rotation, things like that. But they didn't do any manual creation of new images or pull new images from anything. They did everything with the original data set, which I thought was pretty interesting. And then I thought this was probably, to me, was the novel thing they did, was concentrate on those edge cases, those really hard cases, and give the model more examples like this to help it.
So I like this that they look at the difficulty score and make sense, but what did they do? Something around the distribution? They didn't just remove the hard ones, right? They look at their distribution.
No, they added more. They added more of the hard ones.
They added more because
yeah,
lower. Okay, it said that they look at the distribution of the hard ones and try to match the validation set in a similar way to the training set.
Oh, right. They wanted to distribute the hard when they create these new ones, right? So they're adding 880 new images, right, and removing 880, right? So they look at the difficulty score for each class in the training data, and they want to match that distribution in the validation. So they want to keep it, when they add more and take more out of the training set, they want to do the same thing and maintain that same distribution in their validation set. Otherwise, they won't know if they've really improved, right?
So the whole challenge is you need to give as an output, what is it, 10K images, and
yeah,
some of them need to be training, some of them needs to be validation. That's the whole
right.
output.
You get to choose that, yeah.
And you get to choose that, yeah.
Yeah.
And it has to be the same. Is there an augmentation process used in the defined training, or is it always the same 10,000 images each epoch?
I think it's the same 10,000. Yeah, they're not all the augmentation is
augment on the fly.
Yeah, all the augmentation is done in the pre-processing, right? You're doing that ahead of time.
Yeah.
So really, your submission here is just the 10,000 images and a selection of which ones are validation.
Right. That's right. Yep. Okay. And here's the first place. Ifakar Roy got the first place, and he did some really neat things, I thought. So here's some examples of the actual data, training data. So the very first thing he did was he removed noisy and ambiguous images and fixed. He removed noise from the Roman numerals, and he doesn't tell how he did any of this, but my understanding is he actually sets up a separate image to capture the noise that he's removed, as well as the new image that's denoised, right? So he's and you'll see how he uses it later, but he's actually saving that noise image. So he talks about here, after we remove the noise, we're left with two sets of images, one clean and one noisy. At first I thought, okay, you started with a noisy one, so did that mean you did but apparently he's removing the noise and keeping it as a separate image. So we'll see where he uses it later on, but it's an interesting thing. He doesn't tell how he does this. I mean, I know you can do like denoising with like auto encoding and things like that on images, but I've never heard of actually pulling the noise out. He must do a difference after he does the denoise.
Right.
Yes.
Like he calls them foreground and background, right? Some kind of like
Yeah.
instant segmentation or something.
Yeah. So he must keep a difference, and that represents the noise that he's pulled out. Okay. So then he does this cropping. He talks about, cropping them to make, that's one of his augmentations. Then he does some other kind of fancy data augmentation, which is interesting for images. I mean, he does this process of skewing them, which is kind of neat the way he does that.
I like that. Yeah, that is so cool.
Yeah. And then he does scaling and shearing, which we're familiar with. The next thing he doesn't really talk about how he does this, but it's pretty cool. He adjusts the gray boundaries around the numerals. And the idea here is that it's to simulate brush strokes with varying pressures that people might write with. But not how I don't know how he does it technically, but that's pretty cool.
This is where AI and art meet.
Yeah. And then of course it's all this augmentation is controlled by random seed and things like that. So at this point he's got a bunch of augmented images. He's also got these noise images that he's got off to the side. And now he's going to look at things like this. This is where those noise images are going to come back into play, right? So he does two workflows, right? He's going to put them back into their original backgrounds, but he's also going to use the backgrounds extracted from other images and do things like rotate them by 90 degrees and flip them and do some augmentation of the noise. So he's kind of like creating different backgrounds, right? He's creating different backgrounds to put the same images in there, but so this is his way of producing more data. I thought it was pretty novel. He did use these two differently, right? Occasionally, the second one where he uses the noisy background in cases where there's heavy noise, he likes to use that. The first one for the second. I'm not sure how he identified each, considering that he removed the noise, but maybe look back at how much noise he removed the first time. Maybe that was what he was looking at. And then he shows some of the things where he used this.
So you see here, right?
Is
Like
that
the original one, yeah. I don't know if you're going to talk about this image, but yeah, it's interesting how he splits the foreground with the background.
Right. So here's the first image, right? And he takes the noise out. He's left with the clean image, and he does whatever he wants. He puts it into the background of the second image, right? So now he's got the original, and he's got this one. And he did the same thing with the one on the bottom, right? He put it in to the first one. So he's doing this in a random way. He's just showing two here as an example. And then he might, he also might rotate these images and things like that, right? Flips them. So he does augmentation on the noise also to get other ones. So it gives them a whole bunch of different backgrounds to put the images into. Now he does, this is the one I was thinking of where they use a much higher level model. He uses a much stronger model, not a much stronger, but he uses a stronger model here to then go and do some cleanup of problem images. He looks for images that are really similar, so basically duplicates of each other, and he'll remove one of those. He will remove ambiguous ones, and then also he can identify any mislabeled ones also here. So it's interesting. I thought removing the mislabeled one with a better model was kind of I was like, I don't know about that. But anyway, so it's very interesting. Gives a whole entire labor workflow here. So he was the winner. And the interesting thing I found from most of the other ones I read Because he's basically the only one that never did any manual part of any of the data clamp or anything manual, right? Everything is, all of these are, at least from what I can tell, from what, you know, he didn't detail everything, but from what I can tell, everything is being done through a automated process.
That's cool.
Whereas almost all the other ones use some manual labor to do part of it.
I like the ones that call their relatives and friends.
Yeah. So anyway, some very, very interesting things. A lot of these techniques can be used for any domain, not just you know, image classification. A lot of this data cleaning, even the augmentation things, can be done with many other types of you know, ML type of problems. The error analysis that was done by a couple of them was really, very powerful. So in analyzing how well you're doing and which, you know, really looking at the ones you're missing and trying to understand why and what you can do better. Are there more samples you can generate that would be similar that you could train on? So it's almost, we don't think of it as unbalanced, but it's really like unbalanced on certain hard types of samples that we need to give the model more to learn with.
Did
Anyway.
this first place winner do any error analysis? I didn't see it.
Well, he used his ResNet 152 to clean up
Oh.
some of the problems, but I don't think it didn't mention any kind of real, like, you know, going back and thinking about why he missed anything. The way he presents it, you know, he just did all this as a way to do it, and the other guy, what I thought was good about the other guys is they kind of showed how their error analysis led them to go back and create some more data augmentation. So the winner here, he may have done that. He just didn't detail it. He didn't tell us about it. Right.
Got it.
I mean, he was probably just like the rest of us, right? We'll try something and see if it improves, and then we'll go back and make another, you know, so it's kind of an iterative. I'm sure he did it all in an iterative fashion as well. All right, I will, I wanted to, let me throw the, I'll stop my sharing first.
Sure.
Here's the URL to the competition. If you look at the leaderboard, you can pretty much just type the name of the person and Data-Centric AI, and their write-up, if they did a write-up, will come up right away in Google.
Mm-hmm. Yeah. Any comments, feedback, questions from our friends before we? I have one question for you, which you kind of mentioned multiple times, but I want to give the chance to other people first.
I would ask if anybody, I mean, George mentioned that we may want to visit some of these things in the future, because there's a lot of techniques here that are really neat and could be a whole subject for us to dive into. So if anybody has any interest in any of these, please, yeah, let us know.
That's a good point. Yeah. I feel the winners here. I feel this was like a very interesting computer vision task. So people who had lots of experience with that probably will do better. I wonder how this would look like, you know, for like NLP or like structured data or like audio or something like that.
Yeah, I think, well, that's what I said. I think a lot of these some of these methods are transferable, could be used in other domains. Mislabeled things, identifying mislabels, you know, augmentation. We've actually tried a few augmentation things with NLP in the past, where you can have, there's generators out there that'll misspell words for you, and you can create a whole bunch of different. They even have a few things where they'll synonym replacement, and they'll do a few simple grammatical equivalents, right? So there's you know, you can say something two different ways, but it means the same thing, kind of thing. I don't think they're, you know, that sophisticated, but there are some. There may be even some advantage to looking for mixed language and doing a translation. So if you're looking at something that's being generated online by end users, they may switch languages and use you know, phrases from one language to another, and it might benefit your model to have everything translated into a base language or something. Yeah, I could see there being lots of things you can do with it.
I can see lots of techniques that are applied specifically to the domain, you know, like.
Yeah, it's very domain specific. And you can understand landing AIs, you know, they're looking a lot at introducing quality control type of things where they're looking at images, and so they're very interesting in this type of domain. So they're one of the sponsors. So I was a little disappointed to see that it was actually a vision. I was hoping to see something else, but still, that very novel and interesting approaches.
It's the first competition, yeah, I'm sure.
Yeah, hopefully they'll do another one. Yeah.
But going back to something that you mentioned multiple times, right? As we understood it, that, you know, back in the days, we focused on the code and not the data. Now we focus on the data, not on the code. But as we saw, there was so much code to generate that data that, as you mentioned, David, like, okay, is this like not fair, but is this really what we want? And, you know, is this like a fair treatment? Like, can you rely heavily on code and algorithms and models to generate this data, but then claim that this is a data-centric approach? Or is this a code and data-centric approach? Right. Yeah.
Yeah, that's a good point.
I think it's both.
We only have, yeah, we only have a simple Raspberry Pi to actually train our model with. But when we process our data, we're going to use TPUs and you know,
right,
the cloud services. Yeah,
and we know that from firsthand. Like in this approach, in the code plus data, we know that from the transfer learning approach, where we use like a heavily trained model on, you know, some a cluster of GPUs where somebody spent thousands of dollars training it on a large data set, and we use that knowledge, transfer learn it on a Raspberry Pi. But that's transfer learning, you know. That's
no, I know. Yeah,
yeah.
Well, it does beg the question on how one would measure that comparison, right? maybe total number of CPU or GPU cycles, or
yeah, some kind of limit on the how much money or, you know, resources you can throw at it. Or if they didn't maybe disclose what is the actual baseline model that runs, right? Disclose it was raised to 50. Maybe if they kept it hidden. If they hid it, you don't know what it is.
That would be interesting.
All right. That way you wouldn't go like up or down. I mean, you could assume it's like somewhere in the middle, but
it's interesting because a lot of the winning approaches, they use very similar models to the base, you know, to the one that would be used in the competition. I mean, they wanted very similar behavior,
right?
But yeah, if they didn't know anything about
their choices were biased by knowing that it was ResNet 50.
That's what I'm saying, right?
Suspect. Yeah. I suspect. Yeah.
But then if you, okay, let's say you do all this and you optimize the data so that your ResNet 50 in production performs well, is that the best approach, or is a better approach to just swap the model and the data?
I mean, how do you even compare it though when some of the people are using phone a friend as their data generator, right? That's not scalable at all.
Right.
I like that.
Yeah, it's a one-time thing. That's not gonna...
I mean, you found the golden data set. That's, you know, you've imputed so much universal knowledge, you know, from outside sources there, that this data is like so rich in information at this point. I suspect any decent model will do well if given this high quality data. Cool, yeah. And as you mentioned, coming from landing AI and, you know, manufacturing, and you know how they're detecting defects on like steel sheets here, for example. as well as the value of clean versus noisy. So noise is in dark blue, clean is in lighter blue. So basically you can have, for the same number of samples, you can have higher accuracy. Or if you want the same accuracy, let's say 50 something, 60%, you need like 1200 samples with noisy data, or maybe less than half, like 400, 500 with clean data. Yeah, and this is an article I didn't read it. I just looked at the highlights here, but yeah, basically he's saying that in many industries, giant data set doesn't exist. So he's coming from the industry perspective, you know. So he's saying you need to shift from the big data to the good data mentality. So he's saying that 50 thoughtful engineered examples can be sufficient to explain to the neural network what you want the network to learn. Yeah, so collecting data is useful, but in general, collecting blindly, you know, is a very expensive activity. And he's saying that, you know, in traditional approach, you know, you train it on images from the internet, and that machine learning model serves a billion users. I don't know, some kind of content or intent detection. And in manufacturing, simply because each manufacturer develops slightly different models of slightly different parts, you can have, you know, 10K manufacturers building 10K custom AI models. Like, you know, the scale is very different. Yeah, that was interesting. I also posted on Meetup, there are 2 YouTube videos that I came across. One is this Data-Centric AI real world approaches. I haven't watched the whole thing, but I posted this. This was August 2021. And there was something else related to MLOps. Yeah, I chat with Andrew on MLOps from Model-centric to DataCentric on March 2021. I posted both of them on our Meetup page here. Yeah, this is a really interesting concept, and thanks David, thanks Robert, thanks everyone for participating. I like that winners, you know, or everybody had the chance to share their work. I think we can learn a lot from them. So yeah, we'll definitely follow the field, and we'll improve our knowledge. Like this is what we want to learn, right? How do we pre-process data in a better way? How do we actually augment the data? How do we treat the data in a smarter way so that we can improve performance? So what lessons can we learn from here that we can use in our own projects, you know, here at DeepLearning Adventures or at work or for fun? Cool. That's what we have. If there's any comments, feedback, let me know. But if not, I'll just maybe share what is coming up. So we don't have anything scheduled yet, but we're thinking of doing another event end of this month, maybe on the 30th. Robert, you have your presentation this Saturday, is that right? Is it still right? That date, perfect. So yeah, I highly recommend you friends to check this out. So another organization called San Diego Machine Learning is covering Aurelien Giron's book, the second edition of Hands-on Machine Learning with Scikit-learn, Keras, and TensorFlow. And Robert and I have covered a couple of chapters, and Robert is covering chapter 17 out of 19 this Saturday. I think it's at 3 p.m. Eastern. Yeah, a lot of people joining.
Representation learning, autoencoders, GANs, interesting stuff.
Yeah. Looking forward to it. So maybe we could do another session.
Very high level discussion. There's way more content there than one could cover in an hour.
I'm hoping we could do maybe a follow-up session on the 30th, and that will conclude March. And then for April, we'll definitely come back to the, hopefully by then, the AWS exams experience. I'm training really hard. I'm actually traveling back to Albania and Greece on the 25th. I'm hoping to take it next week. I'm hoping, but if not definitely on the last week or first week of April, last week of March or first week of April, take the exam. Cool. All right. That's all we had. Again, I'll post the links. The recording will be available here on guest speakers, and we'll resume our AWS machine learning specialty pretty soon. Stop sharing and stop recording at this point. Thanks, David. Thanks, Robert. Thanks, everyone, for participating. I'll leave the floor open, but I will stop the recording. For everyone joining us on YouTube, thanks again, and keep in touch. We look at your comments and your feedback. Thanks.